So let us start the discussion. So we were discussing this basic structure of a classifier using discriminant function. The concept I'm just revising once again with the help of this diagram. So input is a vector x like this, and this x is going to different functions like g1, g2 up to gcx. That is so many classes. You see here represents number of classes. So once I apply input to all of these functions one at a time, then they will produce their output. Suppose this is 10, this is 5, this is 6, and so on. And I just choose then who is max out of this. Say, well, this one is max, so I will declare my input belongs to class 1. So that is the simple concept we are using here. Suppose I apply some new input, say x2, then suppose this is 15 and this is 6 and this is say 8, then winner is this one. So I will say this belongs to class 2. So this is a very simple concept to design a classifier. Now what we are going to do with this gx, I want different GIs, where I stands for number of classes, say 1 to C. So if my system is needed to recognize say 0 to 9 numbers, okay, that means there are 10 classes. Okay, so that means I will require G1x, then I will require G2x, and so on up to G10x. Okay, say for example, I want to recognize letter A, say this A to Z's, then there are 26 classes. Then I will require G1x, G2x, and so on up to G20x. Okay, so concept is very simple. We have to have different functions representing different classes. So each function is responsible for one category. It will represent one number or one letter. Okay, so when I apply input feature x, the function which recognize or which produces largest output will be declared as the class of input. Okay, that is the concept. Now here this g or this function gx, we are designing using base. Okay, we are using base to decide what is gix is for our problem. You can have your own method of doing this. So we will see in neural networks, when you will learn artificial neural networks, same thing, same functions, we will come out or design using ANN algorithms. Now, right now we are studying the classical way of doing this. So we are using Bayes method to find out G1x or GIX. So then we have seen the way of doing it, say in case of a two-class problem. So we can generalize the things. If we are able to do in two-class problem, we can extend this concept to 3 or 4-class problem. So the concept we took then forward for just only two-class problem. And then we saw a decision boundary can be found out, or you can have a decision boundary maybe like this for two classes. Then the concept was extended or generalized for multivariate functions, that is g of x, where x is d-dimensional. When x is one-dimensional, I will write it like this. When x is d-dimensional, I will write capital X. So when x is multi-dimensional, we are using a normal distribution, or we are assuming that our data is normally distributed for all classes. Here there are two classes, so I will have N1, that is normal distribution represented by say class 1, then it will have its mu1 and sigma 1. N2, then it will have its mean, it will have its own covariance matrix. Okay, so this is the way we represent our data. So say there are 100 samples belonging to class 1, okay, and 100 samples say belonging to class 2. Then we take this group of class 1 and find out corresponding mean and covariance matrix. Then we take second set of class 2 and then we find out mean and covariance matrix. So once this data is processed, I will get two equations, say n1 and n2. N1 represents class 1 then, and n2 represents class 2. Once this is done, our data model is ready. Then we use our normal distribution equation further to find out the decision boundary between two classes that we have seen yesterday. And we have seen there are three cases. So case number one is that this covariance matrix is same for all classes, that is sigma 1 is equal to sigma 2, and that too sigma 1, which looks like this, sigma 1 1 square, sigma 2 2 square, and so on up to sigma dd square, and that too sigma 1 1 square is equal to sigma 2 2 square, and so on up to sigma dd square. So this is our assumption. That what this indicates is that there is no relation between two variables. Say x is my feature vector, then x1, x2 up to xd, these are extracted features for the given say letter or number, whatever you say. But there is no relation between x1, x2, there is no relation between x2, x3, and so on. They are all independent. When they are all independent, these off diagonal entries will be 0. Okay, these off diagonal entries will be 0. That means there is no relation between the two variables. Say this is representing x1, x2, x3, so on up to xd, and these rows are also representing same thing. So this particular point is the relation between x1 to x1 itself. So x1 to x1 itself is related to spread of x1. So this variance is representing spread along x1 axis of my data, and this 0 here represents that x1 and x2, they are not related. So there is no relation between the two variables. That means if x1 is increasing and then x2 may be increasing, this may be the situation. Or there may be a situation x1 is increasing, then x2 may be decreasing. So this kind of relation do exist in many variables, but when I write here 0, that means there is no relation between two variables. I don't feel that there is a relation, so I can put there 0. Now what this sigma 2 2 square is representing? Sigma 2 2 square is representing spread of your data along x2 axis. Okay, so like that, sigma dd square is representing the variance of your data in dth dimension. Okay, so we then assume these two things, that sigma is same for all, and that too sigma 1 1 square is equal to sigma 2 2 square, and so on. So these diagonal numbers are same. So it means that spread along x1 axis and spread along x2 axis is same, which results into a circular shape, kind of a shape, when you see from top this Gaussian distribution. Okay, so if you see a Gaussian distribution of say 2 dimension, it may look like this. Okay, you can imagine like a cap, and then when you see from top, say from here, then you see n circles from top. Okay, these are equi-valued circles. So this indicates that spread of this x1 variable and spread of this x2 variable is same, so it will result into a circle. If it is not same, what will happen? You may have this elliptical kind of shape. Okay, you can have this kind of shape. Okay, so you can imagine that this cap is compressed along say x1 axis. So this is a less spread, this sigma 11 square, and this is a big spread along x2 direction. Okay, so this will be sigma 22 square. So depending on the value of sigma 11 and sigma 22, it will look, say if I take this diagram, then sigma 11 square is more than sigma 22 square. Okay, so here what we have assumed, that we are assuming this particular situation, right? So then we solve this for the decision boundary. Our target is to find out decision boundary. The decision boundary of this we found out with the help of this normal distribution equation. And when I take 1D case, when I took the 1D case, it will resulting into a threshold like this. When I take 2D case, it is resulting into this boundary which is lying over here. When I take 3D case, then it is resulting into a plane like this. So this plane is shifted if I increase the posterior probability. Okay, so we are interested in finding these planes, or we are these lines in this case, or threshold in this case. So then once I obtain this, I can remember parameters of this plane or parameters of this line or this single number threshold, depending on the situation. Once it is done, then I can throw my all data. I don't require that anymore. Whenever now a new test sample, suppose X test is appearing here, what I will check whether this is below this line or it is above this line. If it is below this line, it is the region of omega 1. If it is above this line, this is the region of omega 2. Same is the case with this planes also. If you are above this plane, you are in omega 2, and if you are less than this plane, then you are in omega 1. So this side of this plane is representing, suppose, letter A, and this side of this region is representing class B. Okay, so this is a two-class problem. Now you can assume there are, say, many classes, then you have to have different planes, okay, representing different zones or characters that you want to classify. So this is the second case, I think. So this is case number 2, where sigma matrix is same for all, but you can have sigma 11 square not equal to sigma 22 square, may not be equal to sigma 33 square and dd square. So this is the more generalized version of the first right situation. And then we have found out decision boundary for this, and it is also the same one. Only thing is that this angle between the two center and this line is not now 90 degrees. In earlier case it was perfectly 90 degrees, but this is not the case here. Now these planes are now not passing through the center of this line joining these two centers. So that is the only difference, and they are not perpendicular actually. Then we have seen the more generalized case that everything is different. That is, sigma matrix is different for different categories, and that two diagonal elements are different. That becomes my most generalized version, which gives me a curvy shape kind of or parabolic kind of shapes of boundaries. These are all non-linear boundaries. Okay, so the decision boundaries are non-linear, and this is what ex we expect from a classifier. Classifier is useless if it is just able to draw lines. Okay, that means it can handle only linear problems. A classifier is useless if I have this classifier which can handle only linear problems. Most of the real life problems are non-linear. Okay, so then since most of the problems are non-linear, I must be able to draw some non-linear curves between two classes. Now this is class A and this is class B. Okay, or maybe there is more difficult situation like this. Okay, so this boundary between the two classes is non-linear. So I must be able to draw decision boundary like this. Then you can see different situations that are shown here for different values of sigmas and this covariance matrix. You can have very good nonlinear surfaces between two classes, even like this or like this. Okay, like this. You can see different shapes here. So go through this Duda book for this particular topic. Okay, so we have different shapes over here that you can see and understand what happens if I take arbitrary values of sigma. So now when I extend this case for multi-category, that is I am say here extending this for 4 categories, you can see there are 4 normal distribution curves. So this is first one, second one, third one, and fourth one. So I have n1 mu1 sigma 1, then n2 mu2 sigma 2, then n3 mu3 sigma 3, and n4 mu4 sigma 4. So this is say n1, say this is n2, this is n3, and this is say n4. So I have 4 classes, and each class is represented by its own normal distribution curve. Now when I take the Bayes rule for decision, then you will see that at the bottom you can see this is the region formed due to this intersection of different curves, and this side I think is shown as R2 or so, or region 2 or region 1 here say, and this is region 2. So this is class 2, and this may be class 3, this may be class 4. Okay, so different regions are formed due to this intersection and implementation of Bayes rule. Okay, so this is a scenario when you take multi-class and multivariate data. What is the meaning? Multivariate. Multivariate means you have more than one or two variables. In this case, there are 2 variables. So when your input is more than one variable, say it is of this form, it's a d-dimensional vector as your input. What are these x1, x2? Say this may be height of the object, this may be length of the object, okay, this may be depth of the object. So these are different variables that we have selected from our knowledge, and that when I give you some object like this, say this is the object, then I measure height of this, I measure width of this, I measure depth of this. So this object here onwards is represented by three numbers, x1, x2, x3. Somebody say, okay, this is not sufficient, I will measure something else, say weight of this object. Then you have fourth one as weight. So you can keep on adding such kind of features your problem if your problem is not solved with the help of less number of features. You can add more features. Okay. So if you add more features, then your dimensions of data will increase. So in that case, we will call this problem as multivariate problem. And then we assume that this data is distributed in normal form or Gaussian form. Then we assume this this normal distribution curves, or we try to fit normal distribution curves on this data. Okay, so this is multivariate. When it goes to many categories, that means I want to recognize, say, number one, then number two, number three, number four. So I have now four classes, say class one, class two, class three, class four. Then my problem is multi-category. More than two is multi-category. Minimum, at least you should have two classes. Otherwise, there is no fun in doing this. So you have to have minimum two classes. You can have many classes in your real problems. Now try to solve this problem and you can discuss me in tomorrow's class. I will give you the discussion or hint how to solve this, but you will try at home how to and find out the answer. I am giving you answer, but you will solve and get this equation. Okay, so this is the final answer. Question is, find out, you can note down this, find out the decision boundary, find out the decision boundary between two classes, between two classes. The class details are as follows. So for class 1, mu1 is 3, 6. Sigma, the covariance matrix, is half, 0, 0, 2. Okay, so this is data about class 1. So it is assumed that N1 is normal distribution with this mu1 and sigma 1. Okay, then we have data of class 2. Then we assume that this is a normally distributed situation again with mu2 and sigma 2. Now if you see actual data, see there are 4 samples you can see here which are belonging to class 1 and 4 samples belonging to class 2. So if I take these 4 samples and find out mean, so mean will be appearing somewhere here, right? And mean of this second group will appear here. So this mean is given to me as mu1 and this mean is given to me as mu2, which is written over here. You can even check this with your you can check visually what is value of this. You can see this is 3 over here and this is possibly the 6. Okay, so this is mu1. Similarly, mu2 is 3 over here. This is 3 here and this is something, say, -2. Okay, so maybe -2. So this is given to us as mu2. So mu1 and mu2 is given to us, and then based on this 4 data samples, we have computed this covariance matrix. Okay, so we may take one example later on how to compute this covariance matrix if you are provided with only data. So you can remind me maybe tomorrow that we have to take this problem, so we will take this separately. Right now it is given to you ready-made, and we will take it as it is. So this is sigma 2 for group 2 and this is sigma 1 for group 1. So everything is known to us. Now question is find out decision boundary. So this is my question. Answer is here. The decision boundary is given by this, and this parabola is actually the decision boundary. One more data is given to you is priors are equal. So these priors are equal. Then how it will look? And answer is this, it will look like this. Now how to obtain this equation, that is x2 is equal to 3.514 minus 1.125 x1 plus 0.1875 x1 square. How to obtain this? So go back to your basics and you choose this equation for multivariate. This was the multivariate distribution equation, normal distribution equation. Everything is known here. This D is 2 in this case because we are solving two-dimensional problem. Sigma is given to us for both classes, so this is known to us. Mu is also known to us, so there is nothing unknown in this situation, so we can proceed. And how to obtain mu, the procedure is given over here, you can go through this. And how to obtain covariance matrix is also given here. Okay, so this is outer product, average of outer product of the differences between samples and their respective means. So if you do that, you will get covariance matrix. Now I will give you some hint how to find out. So this is your normal distribution equation. Then you will find out, say, G1x, and then you will find out G2x. G1x you will equate to G2x. And thing is that you are going to use base. So that means what is expected is that you will equate posterior probability of omega 1 given x is equal to probability of x given omega 1 into probability of omega 1 divided by probability of x. Then probability of omega 2 given x, so these are posteriors, equal to probability of x given omega 2 into probability of omega 2 divided by probability of x. Now we are declaring these two things, posteriors, as suppose G1x and this as G2x. You will get boundary whenever you equate these two discriminant functions. Okay, so I am going to equate these two now. I can rub this. So this posteriors, when I equate, I will get this equation. Okay, so this probability of x and this probability of x will get cancelled out. And from the problem, it is given to you that probability of omega 1 is equal to probability of omega 2. So this will also get cancelled out. So what is left is only this, these two things. So probability of x given omega 1 is equal to probability of x given omega 2. So this we have to solve. And what are these two things? These two things are nothing but they are likelihoods of class 1 likelihood, and this is class 2 likelihood. That means they are the data models of class 1 and class 2. So what we have assumed here is that this data is normally distributed with n1 mu1 sigma 1, and this data is normally distributed with n1 n2 mu2 sigma 2. Okay, that means we have to equate n1 mu1 sigma 1 is equal to n2 mu2 sigma 2. Okay, so if you equate and simplify, you should get this boundary equation. So how do you do this? So you take this basic equation, then you write this as 1 by twice pi. D is 2 here, so D is 2, so 2 by 2 is 1, so I just write 2 pi into sigma 1 mod square root of that. So this is determinant, actually determinant of sigma 1 square root of that into e to the power minus half into x minus mu1 transpose sigma 1 inverse x minus mu2. Okay, so this is now equal to, so this will be equal to, I'm just writing downside, but this is equal to 1 by twice pi determinant of sigma 2 to the power half into e to the power minus half x minus mu1 transpose sigma 2 inverse x minus, sorry, this should be mu1, this should be mu2. Okay, change this now, there is some error here, so this is mu1. Okay, so when you do this, now you substitute all the values in this equation. Say number 1, values is x, you will substitute with two variables, that is x1 x2. Mu1 you will substitute with this, sigma 1 you will substitute with this, mu2 and sigma 2. So substitute all this. This obviously this 2 pi will get cancelled out. You need to calculate this quantity separately, that is determinant of sigma 1, determinant of sigma 2, and this inverse of sigma 1 and inverse of sigma 2. So before you solve this equation 1, you have to find out these two quantities. Inverse of a 2D matrix. If it is 3D, then you have to find out inverse of 3-dimensional matrix. If it is 4-dimension, then you have to find out inverse of 4-dimension matrix. I hope you recall that. What is inverse? Inverse of a matrix. So if I take sigma multiplied by sigma 1 multiplied by its inverse, it will give you identity matrix. Okay, so you have to find out then inverse of this. So you can check on net, or you can go to your basic book of mathematics how to find out this and try to put here. Okay, and when you simplify this, you will get this particular equation. Okay, once you get that equation, use your knowledge about this curve, the parabola curve, and if this is the parabola, then you can find out vertex, that is say x1 and y1. So x1 is obtained with this equation minus b by twice a, and then you can put this x into this parabolic equation and find out y. You will get this two say values, and that will be vertex of your parabola. So you will get then, or you should get basically this particular point here. So you will get this particular point. Okay, this is your data for that vertex. You require ABC. So this ABC, this A is coefficient of this x square, this B is coefficient of x, and this is C. So you go to this. So this is a reverse order. So this is your A, this is B, and this is C. You use this ABC and find out this vertex point. Okay. So this is exercise for you. You will try to solve at home today and tell me any problem tomorrow. Okay. Let us stop here.